So in the previous videos, we looked at finding recurrence relations and describing recurrence relations. But in this video, we're gonna work on finding the general formula. And actually, there's many ways to find the general formula. And in this video, it's just gonna be a relatively simple technique for finding basic recurrence relations and finding the general formula for recurrence relations. So we're gonna look at an example that we looked at before. So let's say I'll put it in blue. No, actually, I'll put it in red. We're gonna look at this again. So you want to find the general formula for this recurrence relation. And as we found before, we know that it was an plus 1 equals an plus 2 times n. That was our recurrence relation formula. But we want to find the general formula this time. So what we do is, since we can see that, I'll just show you at first, and then you'll understand why I do this. So A2, using this formula, we know that A2 is equal to A1 plus 2 times 1. And then we know A3 is equal to A2 plus 2 times 2. And we know that A4 is equal to A3 plus 2 times 3. And then if we keep stacking these equations, then we're going to reach an equals an minus 1 plus 2 times n minus 1. So there we go. So basically we just stacked these equations. And why are we doing this? So if we add all of these equations, you can see that all of these cancel out. All of these terms, they all cancel out, except for A1 and AN. So yeah, as soon as we see that AN plus 1, a term is equal to some term plus some formula, then we kind of stack these equations and add them all together so that these all cancel out and we get a general form. We're only left with AN and another term, which is pretty obvious. So yeah, if we add all of these equations, these all cancel out and we get AN is equal to A1 plus 2 times 1 plus 2 times 2 plus 2 times 3 all the way up to 2 times n minus 1. So this is just equal to, using the summation symbol, k equals 1 to n and 2 times k. Oh, n minus 1, sorry. From k equals 1 to n minus 1, 2 times k. Sum over that. And that is just equal to, and we can just simplify, we can take the 2 out, and if we, using that formula where we add from 1 to, using the, what is it called? Yes, summing from 1 to a positive integer, we get 2 times n minus 1 over 2, and then simplifying that, A1 is equal to 1, and the 2's cancel out, and we get 1 plus n squared minus n, and therefore, just putting it in order of the degree, an is equal to n squared minus n plus 1. So in conclusion, an is equal to n squared minus n plus 1, and that is our answer. So there you go. So that's a relatively simple way of finding a general formula for recurrence relations like this. And actually there's more complicated ways to do this, like some characteristic equation and non-homogeneous equations and stuff. But yeah, if you get some equation like this, and you know like the formula for when you sum this formula from n equals 1 to n equals n, then you can just use this method to cancel everything out and then get a simple formula. So yeah, that's one way to do it. And actually, yeah, let's do another example then to get this to make this more straightforward. So, okay. So our next, pencil. So next example is 1, 2, 5, 10, 17, and so on. So yeah, I'll leave you guys to do this on your own, or yeah, I recommend you to pause this video and try it on your own first. And you're back. So the solution is, so first, yeah, you probably should have found the recurrence relation first, and you can easily find that. I'll just skip over the details. You can easily find that the recurrence relation is an plus 1 is equal to an plus 2n minus 1, because if you look at the differences, it will just be 1, 3, 5, 7, and you can easily find that that's just equal to 2n minus 1. So yeah, that's the recurrence relation. And then we're going to do the same thing again. So we're going to stack these equations. So a2 is equal to a1 plus 2 times 1 minus 1. a3 is equal to a2 plus 2 times 2 minus 1. I'll just do it up to there because it's pretty straightforward. And an is equal to an minus 1 plus 2 times n minus 1 minus 1. And we're going to, like the previous example, we're going to add all of this. Add all these equations. So if we add all of them, again, like the previous problem, these are all going to cancel out, and we'll just be left with an is equal to a1 plus the summation of from k equals 1 to n minus 1, and 2k, summation of 2k minus 1 from 1 to n minus 1. So yeah, and if we simplify that, wait a second. Oh yeah. Yeah, and if we simplify that, we get a1 plus, if we split and simplify the summation, then we get this, and then a1 plus, and using the formula for sum of integers from 1 to a positive n, from 1 to n, it will be 2 times, which is n times n minus 1 divided by 2 minus n minus 1. And we know that a1 is equal to 1 again in this case. So 1 plus, and that'll just be n squared minus n plus 1 if you simplify and expand the brackets. And that'll just lead to n squared minus 2n plus 2. There we go. So our general formula for an is basically just an equals n squared minus 2n plus 2. So that is our general formula for this recurrence relation. So yeah, that's how it works. So this is a very basic so now it must be pretty straightforward to you when you have this kind of recurrence relation. You can just sum over all the equations from the base case to the general case, and then you'll get, and if you simplify everything, you'll get a general formula. So yeah, that is one of the most basic techniques for solving recurrence relations. So yeah, now let's look at one more example, which is a bit more complicated. And we're going to look at the Hanoi Tower problem, actually. We're going to go back to that problem. So if you haven't watched that video yet, I recommend you to go back to my playlist and look at that video, because you'll need it. Because I'll just skip over the details for now. So we found that for the Hanoi Tower, the recurrence relation was an equals 2 times an minus 1 plus 1. That was what we have found. That was the recurrence relation. And this one's a bit different because if we sum over it, if we like stack the equations, it doesn't exactly cancel out, so it doesn't really work. And well, there is a way to do the same technique, to use the same technique to cancel them out. But but that gets a bit messy. So we're gonna look at a bit more interesting way to do it, and not that common, but it's still pretty interesting. So firstly, we're gonna see a pattern. So, oops. So from that formula, we get that an plus 1 is equal to 2 times an plus 1, and an is equal to 2 times an minus 1 plus 1. So again, we're going to add these equations too, but it doesn't really cancel out, but you'll see something, but something's going to happen. Okay, I'm going to just use a straight line. Okay. We're going to see a pattern. So if we add these two equations, we get, no, not add, but subtract. If we subtract these two equations, we get an plus 1 minus an is equal to 2 times an minus 1. And now you'll understand why we did that, because we can see that, we can kind of see a recurrence relation. So if we set this, okay, here's where the magic begins. So if we set this as Bn, so let's say that Bn is equal to an plus 1 minus an, then what will this be equal to? Well, if Bn is equal to an plus 1 minus an, then an minus 1 is going to be equal to Bn minus 1, if that makes sense. Because so an plus 1 minus an is equal to Bn, then if we decrease each of these subscripts by 1, then again, we have to decrease the subscript by 1 again. So it will be Bn minus 1 equals this. So yeah, we found, so then this simplifies to, this easily simplifies to, oops, Bn is equal to 2 times Bn minus 1. And then here you're going to understand why we simplified this, why we simplified it to like Bn and Bn minus 1 and so on. Because so this means that we multiply 2 to the previous term to get the next term, which means that this is a geometric sequence. That Bn is a geometric sequence. So we multiply 2 to the previous term to get the next term. And B1, the base case, the first term is just equal to A2 minus A1. And A2 is equal to 3 from the previous video, and A1 is equal to 1. So B1 is equal to 2. So from these two, we conclude that Bn, by the general formula for geometric sequences, is 2 times 2 times 2 to the n minus 1, which is just equal to 2 to the n. Yeah, that's the general formula for geometric sequence. For a term of the geometric sequence. So yeah, Bn is just equal to 2 to the n. So what we get is that, so if we just plug this into here, if we just plug that in there, we get that an plus 1 minus an is just equal to Bn, which is equal to Bn, as we showed it here before, which is equal to 2 to the n. So an plus 1 minus an is equal to 2 to the n. And then if we rearrange it, we get an plus 1 is equal to an plus 2 to the n. And there we go. We have the same structure as the previous two problems. So like an plus 1 equals an plus a certain formula where we're going to know the formula for summation of. So now that we have a simpler formula, for an easier formula to work with, now we can use that same technique where we just stack the equations and add them all together. So if we do the same thing again, a2 equals a1 plus 2 to the 1, and then a3 is equal to a2 plus 2 squared, and a4 is equal to a3 plus 2 cubed, all the way up to an is equal to an minus 1 plus 2 to the n minus 1. And if we add all of that, again, like the previous two problems, these are all going to cancel out. And we're just going to be left with an is equal to a1 plus the summation of the summation of 2 to the k from k equals 1 to n minus 1, this row, this column. And that is just a geometric series. So again, that'll just simplify to a1 is just 1, and that is just a geometric sequence with first term 2, and common ratio 2. Pretty simple. So it'll just be r minus 1 is here, and r to the n minus 1, and that'll just simplify to 1 plus 2 to the n minus 2, which is equal to, which simplifies to 2 to the n minus 1. So therefore, in conclusion, an is equal to 2 to the n minus 1. So there is a general formula for the Hanoi Tower. So yeah, that was a bit more complicated than the previous two problems because we had to do some other stuff to end up with that structure that we wanted. And yeah, this is a bit more complicated, but it's a bit more interesting to do. Like, if you're more experienced with recurrence relations, well, you'll kind of see that we can straight away do something similar to this here, but we're gonna have to modify some of the equations as we go, and that'll make it a bit messy. But yeah, this is just an alternative way to do it. Another interesting way to solve this kind of recurrence relation. But remember, you can only do this when it's this kind of structure. So this technique only applies for some, only for certain recurrence relations. But in another video, we're going to be looking at a pretty interesting technique to solve a wider range of recurrence relations, where instead of having a term in terms of one other term, it will be in terms of two other terms, like that. Solving the general formula for those kind of recurrence relations will be a bit more complicated, but particularly interesting. So yeah, hope you enjoyed this video, and hope to see you in other videos related to recurrence relations.